In this video, we're going to look at a way of making a new group out of two old groups. Specifically, what we'll do is define a group structure on the Cartesian product of the underlying sets of those old groups. Here's the definition. We have a group G star and H dot, and the Cartesian product of G and H is then to be defined to be the set G cross H, so that's the set of all ordered pairs where the first element comes from G and the second element comes from H, together with a group operation, which we'll just write by writing the ordered pairs next to each other, defined like this. So the product of these two pairs just uses the binary operation of G in the first position and the binary operation of H in the second position. Now you're going to prove that this really is a group in coursework 4, so I won't spoil the fun of doing that exercise by telling you exactly why. Here's what happens when you take Cartesian products of cyclic and abelian groups. The Cartesian product of two abelian groups is abelian. Again, you're going to prove this. In fact, it's an if and only if statement on coursework 5. But the Cartesian product of two cyclic groups may or may not be cyclic. So what we're going to do now is just take a look at an example of the Cartesian product of two cyclic groups not being cyclic. So we'll take two cyclic groups of order 2. In fact, we'll use the same notation for both of them. So C2 will be a cyclic group of order 2, generated by an element X. Now we're going to consider the group C2 cross C2. This is a group of size 2 times 2, which is 4. And its elements are EE, the identity element, EX, XE, and XX. So what we'll do is we'll try and draw up the Cayley table or the group table for this group. So let's switch the right tool on. Here we go, here is our table. And our elements are EE, EX, XE, and XX. And we'd like to compute some products. So first of all, let's work out something like EE. I already said actually this is the identity element, and it's pretty easy to see why. If you do a multiplication like this one, then what you get is EE and then EX, and of course that is just EX again. So this thing really is the identity element. So we can fill in the first row and the first column straight away. This would be EE, EX, XE, and XX, and the same thing down the first column. So now let's do some more interesting ones. Let's do EX times EX. So this is E times E and then X times X. Now X was a generator of a cyclic group of order 2. So X squared is equal to the identity. So this is just EE again. So what we have now just here is the identity EE. And similarly, if you work out XE times XE, you'll just get the same thing happening backwards. So you'll get the identity again. And the same if you do XX times XX, you will get X squared in the first place and X squared in the second place. And that, of course, is the identity and then the identity. So let's just pause before we even work out any other products. Let's just notice what this tells us about every single element in the group. If you look at the square of every element in the group, that's what appears on the leading diagonal, so the diagonal we've just worked out. And you can see we've got the identity element along this diagonal. That means every element of this group squares to the identity element. So every non-identity element has order 2. So this group can't be cyclic. Remember, we showed that a finite group is cyclic if and only if it contains an element whose order is the same as the size of the group. But the orders of the elements of this group are 1, 2, 2, and 2. So there's no element of order 4, and in particular this group is not cyclic. So let's fill in a couple more products. Let's do, what do we have? EX times XE, again just by the definition of the product in this Cartesian product, that's EX, and then XE, which is just XX. Right, so we can put an XX here and also here. Okay, so it's easy enough to complete this table, but the key thing is that it gives us another example of an abelian group which is not cyclic.